Отож, мені дуже приємно оголосити наступну доповідь, яку зробить доктор Рiccardo Cerulli з Національного інституту ядерної фізики Італії, відділення в Римі Вергата. І Рікардо розповість нам про експеримент GAIAS, який лише починається зараз. Це новий проєкт в підземній лабораторії Гран-Сассо, метою якої є вимірювання надзвичайно важливої величини, від якої залежить визначення маси нейтрино і, можливо, інших цікавих параметрів гіпотетичних. Це так звана константа, аксіально-векторна константа слабкої взаємодії, яка в ядрах сильно впливає на процеси, які там відбуваються, і її дуже важко визначити, як виявилось. І от метою цього проєкту є визначення цієї константи. So, Riccardo, you can start, please.
Okay. Good morning, everybody. Let me start saying two important things. The first is I would like to thank Fedor and Vladislav for the kind invitation for this seminar. And the second is let me express my support for Ukraine for this bad time after the Russian aggression. So we are on your side and we support you as much as possible. So after these two things, I think I can start. The seminar is about this new project, and it's called the GAIAS. In this project, we are going to study the axial coupling constant by using crystal scintillator in a low background environment. So in this presentation, I will give you, at the beginning, an introduction to the axial coupling constant problem, let me say, and then I will focus a little bit about the project that is now in a starting phase. So first of all, we can start with an introduction on axial coupling constant. So if we consider the beta decay, we can see beta decays as a mutual interaction of hadronic and electronic currents, and this interaction is mediated, of course, by a vector boson W plus or minus. Of course, as you know, the weak interaction is a V minus A theory, so electronic and neutronic currents can be expressed as a mixture of vector and axial vector contribution. These two contributions have different coupling strength that are generally referred as GV and GA. If we are in the hypothesis, under the hypothesis that the vector current is conserved and the axial vector current is partially conserved, in the case of pre-nucleon, the values of these two coupling strengths are 1 for the coupling GV and 1.27 for the GA. This is what we obtain, for example, for neutron decay in vacuum and free neutron decay. The question is that when you instead have a transition, a beta transition, a beta decay inside the nuclear matter, the value of G con A is affected by many nuclear correlations. And in this case, its value may be quenched or enhanced.
Sorry, Riccardo, one moment. I can see your screen. Maybe it is only me or anybody. Can you see?
No, everything is okay, Slava. It is your problem.
Maybe it is my problem. Sorry.
Presentation perfectly. So please continue, Riccardo.
Sorry for this interruption.
No, don't worry. It's important that we are on the same place. Perfect. So as I told you, in the beta decay inside the nucleus matter, the case of beta decay in the nucleus, so the G con A is affected by many nuclear correlation, and so its values can be quenched or enhanced depending in order to reproduce experimental observation. In fact, if you look on the plot on the right, you can see this is the comparison between experimental and theoretical compilation of energy of beta decay. And as you can see, the probability of beta decay, the time decay. As you can see, the point on the graph are the experimental versus theoretical strength for Gamma-Teller transition, and all the points, in order to interpret, to have agreement between the experimental results and the theoretical expectation, you have to put a value for the axial coupling at around 0.74. Where this value 0.74 is just the ratio between the G con A in free condition over the G con A you need to include in the theoretical formulation in order to reproduce the experimental data. So this plot give you soon the feeling that this G con A is quenched inside the nucleus matter. In particular, the effective coupling constant G con A can be affected by different contribution. The first is meson exchange currents. Then the nuclear medium effect that are because of interference of non-nucleonic degree of freedom inside the nucleus, and also from the nuclear model effect, for example, the so-called many-body approach, like ISM, IBM2, QRPA theory. So the point is that from theoretical point of view, you have all these topics that affect the evaluation of G con A. But if you interpret the experimental data in terms of theory, it is not possible to disentangle these three effects. So you have at the end, by comparing the data with the theoretical expectation, all these effects should be considered, and they cannot be disentangled in one by another. In addition, the G con A is also not a constant for all the atomic nuclei, but they depends on their mass. And as an example, here I have reported this plot in which you can see the effective values of G con A obtained in theoretical beta and double beta decay with two neutrino emission for nuclear mass range from 41 to 136, as they are being calculated in different nuclear models. So you can see that first of all, that there is a general trends on the fact that if you go to higher values of A, the G con A, effective G con A is decreasing, is slowly decreasing. And another point is that, of course, its value depends on the theoretical model that you consider. Or if you want, a different theoretical model predict different G con A value. So this is the trend. There is an important point that it's worth to mention. The fact that there are many nuclear processes that involve in which the coupling constant play an important role, and they have different energy range. Up to now, I have discussed the case, for example, of beta decay, and in particular the Gamma-Teller transition. In that case, the energy range is a few MeV because this process is a so-called zero momentum exchange, because the energy involved in this transition is very small with respect to the mass of the boson, the mediator boson, so are few MeV. In this case, the beta transition, the beta decay depends as a second power of Ga. The same is in the case of two neutrino, two beta decay. Also in this case, this is a so-called low energy process in the sense that the momentum exchange is at the level of few MeV. But in this case, the dependence on G con A is G con A to the 4 power of 4 power. This is because it is a double beta decay, of course. Instead, the other process that is very important and we'll mention also again is the double beta decay with zero neutrino emission. In this case, this process is a so-called high momentum exchange, in the sense that the energy that is transferred is of order of 100 MeV. So it is a different energy range with respect to the previous one, and also in this case the dependence on G con A is that the fourth G con A to the 4 power. Other nuclear processes in which the G con A play an important role are neutrino interactions with matter, like low energy antineutrino and neutrino nuclear scattering, nuclear muon capture, and so on. Also, these are high momentum exchange with different their dependence on G con A depends on the effect that we consider, and then G con A is also an impact for the stellar astrophysics because, of course, for example, the electron capture rate can be reduced in presence of a quenched G con A. So let me say that this axial coupling constant plays an important role in different nuclear processes and in different physical fields. An important point, important process that in which the G con A play an important role is zero neutrino double beta decay. We all know that at the moment in the particle physics, the search for zero neutrino double beta decay is a hot topic because it can reveal the possible Majorana nature of the neutrino and its small mass. It's a way to measure the mass scale of the neutrinos. But it is a major challenge in interpreting the result of a zero neutrino double beta decay experiment because we need, in order to interpret the result, to calculate a very high precision the nuclear matrix element. In particular, in this lab, I have reported the decay, the zero neutrino double beta decay probabilities is reported here. As you can see, the half-life, the inverse of half-life depends on the space factor G from the nuclear matrix element M and M to the square, from the electron mass and the effective Majorana mass of the neutrino, of course, and there is this dependence on the axial vector coupling constant as the GAF to the 4. So, as you can see, the effective value, as I reported also in the previous slide, the effective value of the axial vector coupling constant is a K source of uncertainty if you want to interpret the result of the zero neutrino double beta decay in terms of the neutrino mass. So, in order to, from experimental point of view, we can measure the half-life, but to pass from the half-life to the neutrino mass, we need to know very well the nuclear matrix element and the value of G con A is effective. So, again, what we know from experimental data on beta and double beta decay is that the double beta decays with two neutrino emission. This result, this experimental data suggests that effective values of G con A ranging in the 0.5 to 1 range, depending on the nuclear mass and the theoretical model. So we can see that the G con A play an important role in zero neutrino double beta decay because it has profound consequences. In particular, it can reduce the predicted decay rate by more than 1 order of magnitude because, of course, of this dependence that is very strong. And in addition, it is important to understand the origin and the magnitude of this quenching because it is essential in order to design or to optimize a detector that is going to investigate the double beta neutrino with zero neutrino emission and to extract reliable constraint on neutrino properties once this experiment reach a result of also hidden and also a limit. So the impact of this axial vector coupling, this axial coupling constant, is very important for double beta decay with zero neutrino emission. Now, this is the case of double beta decay. This is a main motivation. The impact of G con A on the double beta decay with zero neutrino is one of the main motivation to study this axial constant. But of course, this G con A also affected the beta decay, and this affected the beta decay in different mode. First, on half-life of beta decays, because allowed gamma transition and forbidden union transition, for this kind of transition, the half-life depends on G con A. And in addition, if we consider higher forbidden non-unique beta decay transition, also the electron spectra shape depends on this G con A. And in addition, just recall that the quenching factor for G con A is a decreasing partial nuclear mass, so it is of interest to study this G con A for different isotopes, for these different nuclei. Now, let me just remind you something about the classification of beta decay. Well, so this way, just to be more precise, what we have in mind when we speak about allowed unique or non-unique forbidden beta decay. Okay, in beta decay, the angular momentum has to be conserved, of course, so we have a nucleus with an initial angular momentum of J and a final angular momentum of JF, plus the angular momentum plus the spin. This law must be conserved. The angular momentum is the sum of the angular momentum of the electron and neutrino, and also the spin, the total spin, is the spin of the electron and the neutrinos in this relation. We call allowed beta decay the transition in which the L is equal to 0, the total L is equal to 0. And we call forbidden beta decay the transition in which this L is larger than 0. In addition, we call Fermi decay, Fermi transition, the transition in which the total spin is 0, while we refer as Gamma-Teller transition, the transition where the total spin is 1. In general, when we have a transition and beta transition, the parity change is -1 to the L. So this is the definition of the parity change in the beta transition. So for example, if we consider allowed Fermi transition, we have total momentum equal to 0, total spin equal to 0. This means this the initial J of the nucleus should be equal to the final J of the daughter nucleus, and the parity change is 0 plus. Instead, if we consider a Gamma-Teller transition, we have a total angular momentum 0 equal to 0, a spin, total spin equal to 1. In this case, so we can have two conditions. We can have that the J initial is equal to the final J, and that the J initial can be also equal to J final plus -1. And the parity, we can have transition with different parities, 0 plus or 1 plus. These two transitions are also represented in the picture on the right. You can see neutron and the decay of neutron, of free neutron into proton. You see neutron with one spin, for example, in a Fermi decay. The neutron is with the spin up, the proton is with spin up 2, and so the electron and the neutrino should have the opposite spin. In this case, you see the total angle, the total spin is 0. And in this case, the nuclear operator does not depend on the spin. Instead, in gamma-Teller decay, you see that electrons and antineutrino have the spin on the same direction, so the total spin is equal to 1. The proton has a spin opposite to the neutron, and so the nuclear operator instead, in this case, depends on the spin. So, from the decay point of view, we can have forbidden unique or forbidden non-unique beta decay. This difference stands on the angular momentums. In particular, we can call forbidden unique beta decay the decay in which the delta J is equal to L plus 1, while the forbidden non-unique beta decay are the case in which the difference from J of the parent nucleus and the daughter nucleus is equal to L minus 1, or delta J is equal to L. So, in this table, the transition are summarized. So we can have a super allowed, so-called super allowed beta decay. This is a pure Fermi transition with L equal to 0 and delta pi plus, parity change plus. We can have so-called allowed beta decay, that is a pure gamma-Teller transition, and in this case, delta J is 0 plus and 1 plus, and then we can have the forbidden beta decay of different level. First forbidden refers to L equal to 1, second forbidden to L equal to 2, and so on. And for each forbidden, we can have Fermi transition or gamma-Teller transition. In red, I have reported the so-called forbidden unit transition, while in light blue, I have reported the forbidden non-unique beta decay. Remember that unique beta decay are the one with delta J equal to L plus 1, while forbidden non-unique beta decay are the one with delta J equal to L minus 1 or delta J equal to L. So in this table, we have in green allowed transition, in yellow the transition that has have high order, the second order, so we can neglect in calculation, and the light blue are forbidden non-unique, and in red forbidden unique. So this is just to keep in mind what kind of transition we have to expect once we know the different, the beta decay. This is just an example how we can compute this decay. For example, imagine we have a difference in the total spin, total angular momentum from parent nucleus and daughter equal to 3 plus. This means that delta J is equal to 3, and the L involved can be 2, 3, or 4. But we know that the parity go to -1 to 12, so this select only L that are hidden, so we can focus, so the transition can happen with L equal to 1 and with S equal to 1, so it is a gamma-Teller transition. L equal to 4, of course, with negligible contribution because it's a higher order. So this kind of transition is a second forbidden unit transition, and in this case, the probability, the matrix element of this transition is proportional to G con A to the square per this gamma-Teller element, gamma-Teller transition matrix to the square. This is the case of unique transition, forbidden unique. If we consider instead the case of delta J 3 minus, this case delta J is equal to 3, so it means that we can use L equal to 2, 3, or 4, but the fact that the parity is negative, select only L that are hot, so we can have L equal to 3 and S equal to 0, so a Fermi transition, or L equal to 3 and S equal to 1, gamma-Teller transition, we can have this both. And this is a so-called third forbidden non-unique beta decay. In this case, you see here, the probability of the transition, the total probability of the transition is the sum of a vectorial part and an axial part. So we have these two contributions, the Fermi contribution and the Gamow-Teller contribution. These two metrics, of course, we have these two terms that are added one to another, and they are the square 2. So if we make the calculation, we see that at the end we arrive with three contributions. One is coming from Fermi transition, one is for Gamow-Teller transition matrix, and there is a terms that couple the two transition, Fermi and Gamow-Teller. This means this has an impact in the kinematics of the decay. In fact, what happens is that in the forbidden unit transition, a leading order, the spectrum of the electrons that is emitted in the beta decay has this behavior. Depends on G con A to the square multiplied for a function that depends only on the energy of the electrons. So you see in this case the shape of the electrons, the shape of the beta spectrum is do not depend on G con A. G con A is only a factor that in some way is rescale this spectrum, but does not change the spectrum shape. And so, in particular, only the half-life of the decay depends on G con A. In the case of non-forbidden non-unique transition, instead, the spectrum has a complicated dependence on G con A, because in that case we have this contribution from Fermi and Gamow-Teller transition. So the spectrum is in this case proportional to these three components. One is for vector coupling, one is axial coupling, and one is depends on the product of axial and vector couplings. So you see that in this case the spectrum is very complicated, and what happens is that also the shape of the spectrum depends on G con A. G con A is not, in the case of unique decay, is a sense you have essentially a universal beta spectrum shape that and the G con A is only a scale factor, while in forbidden non-unique transition the dependence on G con A is very strong, and the shape of the beta spectrum depends on G con A. As an example, here I have reported a few examples in which we can compare allowed and forbidden unique and forbidden non-unique shape. As you can see, there is a difference from allowed transition and forbidden unique transition in the beta spectrum. But most important is the fact that, so as you can see, the shape of the beta spectrum depends on the transition that we are considering. If we are considering allowed transition or forbidden unique or forbidden non-unique transition. And in particular, as you can see that for the case of forbidden non-unique transition, this shape is very much different from the allowed transition. And they depend strongly on the G con A. I can show you this also in so the point, so let me stress this point that the forbidden non-unique beta decays is a way to direct probe the G con A effective value, because the spectrum of the beta depends strongly, also the shape of the spectrum depends strongly on G con A. There is has been proposed in the literature different way to constrain the G-con-A value, to extract the G-con-A effective value starting from the beta decay spectrum. This method is called the spectrum shape method that has been proposed by various authors like Swan and others that are reported there. In this method, you can compare the experimental decay spectrum with the one computed in framework of a nuclear decay model, and in this comparison, you can extract the axial coupling value. So the important thing is that you can consider a certain numbers of beta transition that are of interest for the calculation of G-con-A. So exist in this table, for example, some of them that are of interest for the GAIAS project are reported. You can see there are a lot of transitions that can be considered that are forbidden non-unique with this transition, and the table has been obtained by considering isotopes with high branching ratio with a well understood nuclear structure, and for all this transition, it could be possible to obtain a good extrapolation value for extracted value for axial coupling constant. As you can see, the first, for example, is the decay of cadmium 113, but also the rubidium 87, technetium 99, indium 115, and so on. So there are a lot of transitions that have been considered. The important point, the important issue on this transition is the fact that they have a good half-life, in the sense that the half-life are have a value that allow to have an activity that is measurable in standard experimental condition, and that this transition can be used. These isotopes can be included in some detectors, so they can be measured. And I will discuss it better later. So, just as an example of what I have seen, I have told is the case of the spectrum of the beta decay of 113 cadmium. Here you can see the experimental spectrum that has been obtained in this work that we have done in the framework of Roma experiment together with the group of INFN. So you can see that in this plot you see that the black line is the experimental data, while the colored lines are the spectrum expected in different nuclear models. So you can see some at least two models, ISM and IBFM2 models, reproduce very well this spectrum. It's of interest the fact that there is a small disagreement. There is a small disagreement at low energy. This is something that I would comment later. But as you can see, there is in general a very good agreement, and from this agreement, a value for coupling, for axial coupling constant can be obtained at level of 0.92. So this is the way one can extract by starting from an experimental spectrum, comparing this with the expectation of nuclear models, and obtain extract this value. An important point that it's worth to be mentioned is the fact that, as you can see, these three different nuclear models for a scene produce more or less very similar spectrum. So this means that this is in some way this is an indication of the robustness of the SSM method to extract the axial coupling constant. That is a method that we are going to use also for GAIAS experiment. So now, before starting to discuss more in detail about the GAIAS experiment, I want to record the message is that the hidden non-unique beta decay are a key strategy to measure, to have an estimation on the effective axial coupling constant. So in the GAIAS project, what we want to do is to study the quenching of G con A. We want to measure the forbidden non-unique beta decays in different nuclides by using crystal scintillators. This is the motivation and the goal of this GAIAS project. So first of all, let me recall that our idea is to use a crystal scintillator. So why crystal scintillators are so good to perform such an investigation is because the scintillator are is a solid experimental technique. If you have the crystals, you can incorporate in the crystals beta emitting isotopes. So you have the source of your decay that is inside your detector. So this is very important from experimental point of view because you can measure quite directly the beta spectrum, and the efficiency of the detection is close to 1. With the crystal scintillator, with this technique, you can measure with high accuracy the spectral shape of the beta transition. You can extend this spectral shape at a low energy because you can work with very low energy threshold. And as I showed you before, the behavior of the beta decay spectrum at low energy is very critical. So it is important to select a technique that allows you to use a very low energy threshold. The energy resolution is quite good. So it's you don't need, let me say, a very high energy resolution because what you are studying is a continuous spectrum. So the energy resolution of the crystals can be good for the goal of the project. And so the other point is the detection efficiency is very high because the beta emitter are inside the detector. And finally, another key features from the experimental point of view is the fact that the crystals are very stable, and you can control very much the systematics and the uncertainties that are intrinsic in the measurement because crystals are very stable, so you can have data taking in very stable condition. You can perform calibration in the same condition as in the measuring in the measure, and you can control the Regli scale very, very precisely, and even the energy threshold very precisely. So these are all key features that are fundamental to make a measurement that is with a very, very low systematics. We have performed in the framework of the DAMA experiment in collaboration also with the INFN Kiev group, some result in the few years ago and in our activity in the last, let me say, 10, 20, 15 years, by using various crystal scintillators. In particular, let me remind the result that we have performed with 113 cadmium. That is for forbidden non-unique transition. This result is reported in the plot that is shown in this on the right. If you see, this is this beta spectrum of cadmium 113. We have published in this PRC article. It was a very important result. Then we have also investigated the first forbidden non-unique beta decay of 113 beta stable cadmium, and also in DAMA activity we have also investigated the decay of rubidium 87 that is at the forbidden non-unit transition with very low Q value. So in our group, in the GAIAS collaboration, we can see we have expertise and experience in performing investigation of forbidden non-unique beta decay in different isotopes by using crystal scintillator. What we have done so far up to now, the study that we have performed highlighted the importance of careful control of systematic uncertainties. This is the most important point. The fact that we want to measure very precisely the beta spectrum, so we have to control all the systematic of the measurement. And we know that it is very, very important, and this is the most challenging activity that we have to do in our experiment. So it's very important to have the energy calibration, to calibrate the detector very precisely and continuously, to suppress background, to model the detector response, and to have also a model for background. And so all this. So what we can say is that the measurement that we have performed so far can be considered as, let me say, R&D or preliminary result, and we think that in the future with the GAIAS experiments we can perform higher sensitive measurement of the beta spectrum of different beta emitters. Let me remind also the fact that other approach has been proposed in the literature. Of course, the beta spectrum has been measured with different techniques, but I have just to mention these two techniques because they have been proposed and used recently. So just to say that there is a general interest in measuring the forbidden non-unique beta decay. I have mentioned here the case of the COBRA experiment that measured also the cadmium-113 beta decay, and also the ACCESS experiment that has been this project was born in ERC call for ERC experiment, and they studied and they reported so far the beta decay of indium-115, and as you can see the publication is very recent. So just to say that this field is active and there is a general interest in studying the forbidden beta decay in connection with the two neutrino to the double beta with zero neutrino emission. So in GAIAS, we will focus on different beta decay. The plot, the table that I have shown to you slide ago reported a list of the isotopes we are interested in. Some of these isotopes belong to some crystal scintillator. This is, for example, of cadmium-113 that is naturally present in cadmium tungsten crystal scintillator. So, of course, it's clear that we can use this kind of scintillator to study the beta decay of 113 cadmium. This is also the case of 113 metastable cadmium that is present in an enriched cadmium tungsten scintillator, enriched in cadmium-106. This crystal has been developed and has been used also in the activity of the DAMA experiment together with the NR Kiev group. So we have this scintillator, and we can use this scintillator to investigate this beta transition. In addition, we are interested in developing a crystal doped in some way with rubidium that contains this 87 rubidium that is a beta emitter with forbidden non-unique transition, and also technetium-99. The idea is to perform a crystal growth crystal of some scintillator like cesium iodide or sodium iodide, and during the crystal growth to include this rubidium or technetium as a dopant inside the crystal growth as a contamination, let me say, but in this case is a contamination we are happy to include in our crystal in order to have beta emitters inside the scintillator. It is possible, we know that from a chemical point of view, it is possible to realize some crystal scintillator doped with rubidium. This is, for example, the case of the cesium iodide. So we are going to realize such crystal, to develop such crystals in order to perform this measurement in the framework of the GAIAS experiment. So we want to use to incorporate in the crystals isotopes like rubidium, technetium, cesium, and also possible chlorum. That is another beta emitter that is interesting. In this table, you can see a list of crystal scintillators that we can develop, and with the beta decay emitter that can be included in this crystal scintillator. Of course, the visibility of some of these crystals are divided into three categories. Some scintillators are ready to be produced. This is, for example, the case of cadmium tungsten that contains 113 cadmium and 113 metastable cadmium naturally, let me say. So these two scintillators are ready and we can start measuring them. And there are, instead, we have selected some crystal scintillators that can be doped with the beta decay emitters, and they are potentially of interest. We know that potentially they can be produced. Of course, it needs some R&D development in order to dope this scintillator with these beta emitters, but it's something that there are good perspectives to realize such scintillator. Of course, it is clear that we need to understand is how this contaminant affect the performances of these scintillators. This is something that we need to study for the measurement we are interested. There are then other isotopes beta emitters that are very interesting, but that are very challenging to be used. For example, this is the case of cesium-135, because it is not easy to find such isotopes, and also because 137 cesium is not easy to include this in a crystal scintillator and in controlled way and without and performing a measurement that can be used for our case, so with a controlled level of background. But we are going to study also more challenging crystal scintillator. Of course, what we need is the typical activity that we expect to have with this beta emitter is at level of 100 beta, because we don't need to have very high activity, because 100 beta is enough for our measurement. In let me say, few weeks, we are able to perform a very good measurement with assessing beta spectrum with high precision. Okay, then of course we can also again, referring to the table that I have shown you before, there are also other isotopes that are of interest, but with a very short half-life, and so some of them are natural, some of them are artificial. For that isotopes, the study of the beta spectrum is quite complicated, but we think that during the GAIAS project, we will have time to study possibility to perform this measurement with very short half-life isotopes. The GAIAS experimental setup is here reported. As I told you before, the experiment should be in a low background environment, so we want to perform this measurement in a grand sense underground laboratory. This is a underground laboratory, so it is we will work in a ultra low background condition. The shield of the laboratory reduce the flux of cosmic ray about 1 million with respect to the surface, but this is not enough for our purpose. We will include the detector inside a passive shield made of copper and lead. Our idea is to use 15 centimeter of lead and 10 centimeter of copper as a external shield, external passive shield, that will include all this passive shield inside a plexiglass box or PTFA box filled with flushed with ugly pure nitrogen in order to avoid radon inside the setup. The detector that we are going to use, the crystals are very small, about 10 centimeter length, more or less. So the setup is quite compact, and the typical dimension of the passive shield is 65 centimeter per 65 centimeter per 130 centimeter, and the inner volume of the shield where we are going to put the scintillator is about 80 centimeter per 15 centimeter per 15 centimeter. Our idea is to include this scintillator inside a container of PTFA filled with actually pure silicon oil, because this enhances the light collection, and to couple the scintillator with two photomultiplier in order to reach to collect more light to have a lower energy threshold. So, as regards the sensitivity that we can reach in the GAIAS experiment, in this plot I have reported just the two examples, the case of 113 cadmium and 115 indium beta spectrum. These are in this plot are reported the beta spectrum measured with different nuclear models as a function of G con A for these two beta emitters. So as you can see, if you a small variation of the coupling constant G con A have a dramatic impact in the beta spectrum shape. So this means that measuring with high precision the beta spectrum is crucial in order to have a good estimation of the axial coupling constant. So in particular, as you can see, a change in the coupling constant of 0.1 can lead to a detectable deviation in the spectral shape, especially at low energy. It will depend, the difference is more marked. So what we can say is that in our estimation, we can reach an uncertainty less than 10% in the extraction of the axial coupling constant, assuming sufficient statistics and control of systematic. So for once we have selected a nuclear model, we can have uncertainties on the value of G con A effective at level better than 10%. So the goal we are going to reach. A key point in this is the control of systematic uncertainty, because what we want to do is to have a precise profile of the pedal shape. So it is important to perform energy calibration with multiple calibration points across the spectrum, especially we want to have lines at low energy in order to check the stability of the threshold. And so we have in mind to perform calibration by using different sources, producing lines in all the energy range of the beta spectrum. And in addition, we want to study the background measured with the crystal scintillator in order to have a model of background to validate this model of background that is important in order, again, to extract a clean and precise beta spectrum. The project timeline is reported is stable. The project will start this year, so now we are in the very beginning stage. What we want to do is in 2026 we start with the detector development and start some measurement. In particular, we are going to start with the measurement with cadmium tungsten crystal scintillator. So the first data spectrum that we want to measure is 113 cadmium. We have these crystals, so we are able to produce this in very short time, and so we think we can have a first measurement before the summer. And in the meantime, during the 2026, we want to start the development of scintillator contaminated in rubidium. We have contact with some companies that can start this R&D, this production. What we want to do is to study the behavior of some crystal scintillator with different level of contamination of rubidium. So 2027 will be focused on the measurement of this new scintillator that we are going to produce during 2026, and then in the third year and last year, in 2028, we will focus on the analysis and analysis and publication of the result obtained interpreting the beta spectrum that we have collected the first 2 years. Of course, probably we will have also some publication and data release in 2027. We will see, of course. Our idea is anyway to have this in 2026 start R&D for production of a new kind of scintillator, and 2027 collect data, analyze, and finalize the analysis and the publication in 2028. The collaboration is here reported. Of course, there is an Italian collaboration by INFN, INFN of Roma for Vergata, INFN of Roma La Sapienza, and there is this collaboration with the Kiev group of INR. We have worked so far for many years in the double beta decay experiment and in general in rare decays in low background measurements. So let me say this is a very linked collaboration between us and the Kiev group. So we want to continue on this line, on this collaboration, and also this is part of the collaboration, also some theoreticians from Finland, in particular Sezione and his group. And so we are in strict contact with these theoretical people that can help us to interpret our data and to extract the axial coupling constant. So I come to conclusion. So basically, during the presentation, I hope to convince you that elimination of the axial coupling constant is a crucial issue for neutrino-less double beta decay experiment. GAIAS can measure the Ciccone effective value with high precision for various isotopes by using crystal scintillator and exploring also novel approaches and novel scintillators. The experimental technique that we are going to use is solids, and this has been demonstrated by the R&D that we have successfully completed in the past years. And the collaboration brings together all the necessary expertise and experience to achieve the proposed goals. And finally, this project will run for at least 3 years. At the moment, we have funds for the next 3 years, and grants us laboratory give us space and all we need to perform low background measurements. Thank you.
Thank you very much, Riccardo, for a very interesting talk. And please, if there are questions. Vladislav, please.
Thank you for your talk. It's very interesting. And a couple of questions. First of all, there are many scintillators with quite big content of thorium and uranium isotopes from thorium and uranium daughters. Yes, and there can be some, for example, depot events which can be alpha tagged, and there can be some. We can select background from beta spectrum of this, for example, bismuth with alpha tagging of polonium, and with this kind of technique, we can select beta spectrum with quite good precision, with almost no background. So, is it possible to use this in this experiment?
Yes, yes, of course. So this is one possibility, because it is what I said before is that if you look at the table that I have presented, there are many transitions that we can investigate in GAIAS. One of these is the one you are mentioning. The fact that in case of depot events, of course, the alpha can help us to tag the beta events, so to have a very clear beta shape. And of course, let me say more in general, in case in which you have a transition, you have a very short half-life beta transition, that is the idea is that in our case, if you can find a second decay that can be subsequent to the beta decay, you can access to the beta spectrum by tagging events by events. So this is a possible approach that we can consider in order to extend our project, our measurement to various kind of beta emitters that are present as a contaminant in the crystal scintillator. The ones you mentioned is, of course, one of these cases. So, is of course one technique, one approach that we are going to consider in this project.
Thank you. And another second.
Slava, sorry.
Yes.
Sorry, Slava. Let me comment shortly, please. Your very good question. For instance, we can immediately measure bismuth 212 from thorium chain by using liquid scintillator. We already have this experience, because bismuth 212 is not unique, pure forbidden but not unique, and it will be pure beta spectrum. So just one should measure with better energy resolution and with much lower energy threshold. So we surely can measure bismuth 212, which is can be targeted by subsequent decay of alpha decay of polonium.
In our
Okay,
table,
Slava, you
we
can ask your-
mentioned the bismuth 214, but more or less is so the idea.
Yes, also
what
this
I
one-
want to stress is the fact, yes,
Yes, it
tagging
also can
these
be measured,
events.
but unfortunately we have also gamma, a lot of gamma quanta in this case, so it's not so pure.
Yes, yes.
But it's also
So pure,
another
yes.
candidate. But remember that radium is difficult to incorporate inside of liquid scintillator. It's more difficult than thorium. So thorium can be relatively easily added to liquid scintillator. So, but sorry, Volodya, I see your hand, but Slava have another question. Slava.
Okay.
You can
Yes.
ask.
Thank you. Another question is concerning the shape of double beta, two neutrino double beta spectrum. Is it possible to use it in some double beta experiments for extraction information of GA?
Yes, I think that okay. In principle, I think double beta decay with the emission of two neutrinos is a very good process in order to extract the axial coupling. There are two points that I want to press again. The first is that it's not easy to infer the value of axial coupling in zero neutrino double beta decays from the measurement in beta and double beta with emission of two neutrinos double beta decay. This is because these two processes have different energy range. So, of course, it's not so easy to extract a direct measurement useful for the neutrino as double beta decay. But, of course, if we let me say that in GAIAS, we have not idea to study directly double beta decay. But in principle, of course, if you have data, this can be very useful for extract an axial coupling constant.
Okay, thank you. Of
Yes,
course, of course, I meant not GAIAS.
Yes,
I just said about the other experiment with double beta decay.
Yes.
Slava, and remember that in Cupid-Mo we measured double neutrino, double beta decay of molybdenum with very high accuracy and also extract some information about GA. Cupid-Mo already did it. So next question is Vladimir Tretyak.
Buongiorno, Riccardo.
Ciao.
In fact, I have not questions, but two remarks. Could you please show slide 8? Yes, slide number 8.
Okay.
Yeah. You wrote that half-lives of beta decays depends on GA for allowed transition and forbidden unit transition. But in fact, all beta decays half-life depends on GA constant. So what is written in bracket could be removed.
Yes. Okay.
Okay, and another one, slide number. Huh?
Oh, yes, for sure. For allowed gamma transition and forbidden unit. So the idea is that half-life can. The idea is that the fact on the allowed gamma, the meanings of this slide is the fact that electron spectral shape is dependent depend on G con A only if you have forbidden non-unique transition. If you have a gamma transition, forbidden unique transition, the shape is not does not depend on G con A, but just as a factor of scale factor. So only half-life depends on G con A. This is means.
But GA?
Yes, of course. Also another transition is depends, of course.
Okay. And slide number 19. 19. Yes. There is no need to correct something, but just let you know that in Cobra experiment, in fact, they did not measure shape of beta spectrum. In sense that, okay, they see this spectrum for their 64 detectors, but shape was slightly different for each detector. And they, in all their experiments, in first and in the last, they just compare what they measure, firstly with our spectrum measured in Physical Review C in 2007. And after this, they compare their measured spectra with theoretical spectra calculated by Yoni Suhonen. But they never combined their shapes to obtain very precise spectrum, to see that the shape is this one with some correction factor, the values are this one. So their experiment is much not so good as our measurements in 2007.
Yes,
just to draw your attention.
Yes, thank you for this comment. I know very well there are all the aspects you are mentioning for to be mentioned. In this presentation, I don't want to speak too much about other results. The slide was just to show to people that are not in this field that there is a general interest and on measuring beta spectrum for forbidden non-unique transition. Because generally, if I don't know the audience, but for us that we work in the underground physics, it is clear that the G con A play an important role for double beta, neutrino-less double beta decay. So it is a hot topic. But if you speak to people that are involved in accelerators, for example, so they probably don't know that there is still an interest in studying beta decay. And so this is just to say that not that GAIAS is a project that is in a field in which these measurements are considered important, let me say. Of course, the result of Cobra is not is not as robust as our result. Of course, we know very well this. And but okay, thank you for your comment. I avoid to say too much about the Cobra.
Okay. There is no need to change something, but just
yes.
Okay, grazie.
Welcome.
Please, more questions. So, Riccardo, I have some question, but if you show again your presentation, slide number 4, probably. Also for this, it should be stressed that the bolometric technique provide very good resolution. Please show
Yes.
this 19. So just comment that bolometric technique certainly able to measure with very good energy resolution. But as we see, threshold is very high, 100 keV.
Yes.
And this disadvantage of bolometric technique. And also statistic is not so big because very slow detector. So this illustrates advantage of scintillation technique. We can accumulate millions counts per channel, and we can, for the moment, for instance, in our last experiment with cadmium-113 metastate, we achieve 11 keV energy threshold. So it's, but
Yes.
please show slide number 4. This was comment.
Okay.
It's also interesting point that, no, next one, probably, next 5. Yes, that GA is smaller for the larger nuclei, for the heavier nucleus. For instance, for the moment, we have preliminary estimation for GA 0.6. So it's in agreement with this plot in some way.
Yes. Yes. This is the general trend that appear in all the nuclear models. So it is interesting, and also our result in some way seems to favor this solution, these models. As regard your comment, thank you for your comment on bolometric experiment. Yes. First of all, they have not reached a very low threshold, and the second point is also that performance measurement control some systematics is not very easy because, for example, calibration during the measurement for bolometers are not so trivial to do. So it is, of course, a very interesting technique, can be used for the advantages in the energy resolution, and so, but of course there are also some disadvantages that instead in scintillator we have.
And by the way, let me stress that this diagram is also gives additional arguments to measure heavy nuclei. So from this point of view, because we see only A 140 here, but no result. So I think that maybe we can consider bismuth 212 from thorium chain, as I already told about, as one of the priority. Because it is rather easy experiment, just measurement, maybe even not on the ground, but measurements of liquid scintillator with thorium with fast technique, fast oscilloscope, and we can accumulate beta spectrum rather fast and try to. But the question of how much shape dependent on GA, because for first forbidden non-unique decay, it's not so big
Yes.
dependence. But nevertheless, I think it's one of the interesting possibility to measure heavy nuclei for this plot, for instance. So that just comment about. Because
Yes,
unfortunately, in our experiment, when we measure half-life of polonium-212, we measure this very high threshold. But it was artificially set. One can measure this much smaller threshold, much lower threshold, I guess. So this is one possibility which now I see from your talk, and also Slava question.
Yes.
So there are any other question or comments? Volodya Tretyak.
Comment to Slava question. For all measured double beta decay up to now in 13 or dozen of measured double beta, double mu decays, all transitions are from 0+ to 0+, as in allowed beta decays. So you cannot expect that shape will be dependent on GA. In NEMO 3 experiment for molybdenum 100 and in Cupid 0 with selenium 82, they show slightly different shape, but it was not because of GA dependence. It was because of different so-called SSD, single state dependence, and HSD difference. So their shapes were slightly different from below it, but not because of GA, but because of other nuclear effects. To see different shape for double beta, double nu decay, you should at first observe such decays from 0 plus to, I don't know, 2 plus or 1 minus transitions, and they do not exist up to now. They were not observed. Okay.
Thank you. Thank you for interesting comment. But I hope the transitions from 0 to 2 plus maybe not. It is not so easy to observe, and it will not yet good this observation. But I think that the shape will be in future observed, and in this case we will have a tool for extraction of GA. If I correct.
Yes, but just different that with scintillator we can measure something over during 1 month, while for measurement of double beta decay 2 plus we need 10 years of very, very expensive measurements, I guess.
Or we have to increase the mass of the detector very much.
Oh, yes, if we, exactly. If one produce 1 ton detector, which costs
exactly
$200 million.
It could be a proposal for the next.
Yes, after GAIAS 2 or something, GAIAS beta or something like that.
Exactly.
So from this point of view, GAIAS is very easy, very cheap, and then let's hope rather efficient way to explore a GA.
Yes.
Okay.
I want to say that we expect. Let me comment this part that we think that GAIAS is a good environment to study this transition, but also to investigate this novel approach of incorporating the isotopes in scintillator that can be also a technological development that can be of interest in general, and also it can be a place in which we can also have time and to investigate different approach for very particular decays that at the moment seems difficult to study.
Yes, but by the way, we have been discussing yesterday, because this is a 3-day seminar, so we hope today is 2nd day. Yesterday we have been discussing also this problem, and seems to be that there are also a lot of theoretical issues for this, because experimentalists typically consider theory is correct, but seems to be that also theory need to be developed very much. So, because different models provide different GA, and
yes,
and their shape sometimes is very difficult to describe. But in our experiment with cadmium 103 metastate, for the moment, we describe the theoretical spectra very well with our experiment, or vice versa. Our experiment is described very well by theoretical shape, which is surprising for me, because typically its difference is very, very big. So, okay, dear friends, I'm glad to see you here, and at this moment we can finish our invited speaker lecture. Thank you very much, Riccardo, that you agreed.
Thank you for the invitation. Thank you again, and good luck for all. Okay.
Okay.
Bye to all my friends.
Ciao e
Ciao.
buon pranzo.
Grazie.
Well,